Okay, so we're going to move on to finding limits involving the trigonometric functions. We're going to start with the fact that the trigonometric functions, like all our basic functions, are continuous on their domain. And therefore, if we're finding the limit of a function involving a trig function, and that is a value that we're finding the limit is a value in the domain of the function, then we can simply use direct substitution. So for instance here, when we look at this first one, limit as x approaches 5 pi over 6 of cosine of x, cosine is continuous on its entire domain. And so this limit is simply cosine of, replace x with 5 pi over 6. Right? Since the domain is all real numbers, right? It's continuous on its domain. There's no holes, gaps, jumps, or anything. We know that the limit will be equal to the value of the function at that point. Now, I would like you to evaluate cosine of 5 pi over 6 and give me the exact value. There is a review of trigonometry, sort of a help sheet that comes with the textbook. This is it. And you might want to take a look at it. I will probably make this available for tests so that you will have these right triangle definitions, fundamental identities that you should be familiar with, will make use of, and some other identities. And then, of course, the idea of extending the right triangle definitions to the unit circle. And you should be familiar with this and how to find the exact value, say, of sine and cosine. When we look at the points on the unit circle where the radius r is equal to 1, then by these ratio identities up here, we realize that the x-coordinate for any point on the unit circle is the cosine of this central angle theta. So here's the central angle coming up here, 45 degrees or pi over 4. Cosine of that is square root of 2 over 2. Sine of that is the y-coordinate, which is also square root of 2 over 2. Okay, and so, for instance, we were looking at 5 pi over 6. Cosine of 5 pi over 6 is negative square root of 3 over 2, the x-coordinate back here. If you remember, cosine is positive in the first and fourth quadrants, negative in the second and third quadrant. So, cosine of 5 pi over 6 is negative square root of 3 over 2. And that's what I would like you to give as the exact value of this limit. I don't want a calculator approximation for that, so don't use your calculator to find cosine of 5 pi over 6. That is an estimate. I want the exact value. Okay? And if you give me the exact value and then you want to estimate that, I guess that's fine, but that's not needed. Okay? Let's take a look at the next one. The sine function's domain is also all real numbers, so it's continuous everywhere, including 5 pi over 4. So I can use direct substitution. I replace x with 5 pi over 4 times sine of 5 pi over 4. Now what is sine 5 pi over 4? You can look in the unit circle for that. 5 pi over 4 is in the third quadrant. Sine is negative in the third quadrant. And 5 pi over 4, if you remember reference angles, has a reference angle of pi over 4. Sine of pi over 4 is square root of 2 over 2. So this is going to be negative square root of 2 over 2. And multiplying 5 pi over 4 times negative square root of 2 over 2 gives me negative, right? It's going to be negative 5 square root of 2 pi up top over 4 times 2, 8. Okay. I usually like to put the numerical part in front. Remember, when you're multiplying these three things together, the order you multiply them in doesn't matter, but usually I put the, pi is kind of like a variable almost, even though it's not a variable, it's a fixed value. But this is actually the answer now that I'm looking for, right? This is the exact answer. I can't simplify this any further. Okay, so again, that's what I'm looking for, not a calculator approximation of this. Tangent function, it is continuous on its domain. Now its domain is not all real numbers. If you remember the tangent function, tangent is sine x, tangent x is sine x divided by cosine x, and that ratio therefore is undefined when cosine of x is 0. You should be familiar with the graphs of the trig functions, and so this is showing the 6 trig functions. In particular, tangent x you see has vertical asymptotes at pi over 2 plus any multiple of pi, so at 3 pi over 2, 5 pi over 2, negative pi over 2, and so on. But at pi over 4, which is halfway between 0 and pi over 2, we're continuous on that interval. And so I can use direct substitution here as well. Now tangent of pi over 4, if you recall, sine and cosine of pi over 4 are both square root of 2 over 2. Since tangent is sine divided by cosine, this ratio is 1. 1 plus 1 up top is 2. And then how do I take 2 and divide it by pi over 4? I multiply by the reciprocal 4 over pi. And so my answer is 8 over pi. One more example. Limit as x approaches pi over 6. This function again is continuous on its domain, and its domain is all real numbers here. So if I replace x with pi over 6, what's this whole expression here simplified down to? I hope you say 1. 6 times pi over 6 is pi. Pi divided by pi is 1. Sine of pi over 6, that is equal to 1/2. And you should be able to do that. If some of you have that memorized, that's great. But if you know how to use the unit circle or use the trigonometric ratios from the right triangle, you should be able to get that. 2 times 1/2 is 1. 1 plus 1 is, of course, 2. Okay, so those are certainly easy. And we want to realize then that finding limits involving trig functions, if they're continuous at that point, it's pretty easy, direct substitution. However, there are, just like the examples we were looking at in the last set of videos, situations where we get an indeterminate form when we plug in, like 0 over 0. So how do we handle those situations? Okay. In order to do that, we need two particular limits involving sine and cosine to begin with, and then we can look at other situations. In order to get those limits, we need an important theorem that we're going to investigate here first, and that is the squeeze or the sandwich theorem. And this works for any functions, trigonometric or otherwise. And here's the statement. If you have a function, we're looking at h of x, and it's basically trapped between two functions f and g of x. Notice our h of x is always greater than or equal to f of x, but always less than or equal to g of x. And that's true for all values of x near a, except possibly at a. When we say near a, basically we mean in some open interval about a. So for values of x close to a. So a is some fixed value. Notice it's except possibly at a. We may not know anything about any of these three functions at x equal a. Whether they exist at all is not really required for the squeeze theorem. Because look what we're looking at. If the limit as x approaches a of f of x and g of x both exist and are equal to the same value L, and remember when we're taking a limit, this has, this says basically what? X is guaranteed not to be a, right? We're getting close to a, but we're never necessarily equal to a. So that's why we don't need to know anything about what's happening at a. But if both of these limits exist and are equal, then the limit of our function that's trapped between them must exist and be equal to the same thing. And so the essence is these two functions f and g sort of squeeze or sandwich in our other function h so that it has the same limit. Let me just draw an example of that here. So the g of x function, maybe it looks something like this. And let's say here's the g of x function, and so we'll let this be the a we're talking about right here, and then we will have, get my ruler here, so again, I don't know what's happening right at a for g. I have an open circle there. There may be a point there. It doesn't really matter. I'm going to keep it as open. circle there, but just for reference, we'll come over here. If that limit indeed is L, right, this is what the graph would look like. If the limit as x approaches a of g of x is L. And then let's draw the graph of the function f of x, and maybe it looks something like this. Okay. Now, let's see what the possible graph of h of x looks like, and let's see if it meets these requirements, this graph. First of all, it says h of x is always between f of x and g of x. In fact, it says f of x is less than h of x is less than or equal to g of x. So f of x should be less than or equal to g of x. You say, wait a minute, look how you drew this graph. Over here, you've got the purple f graph above the red g graph. So f is now above, is greater than g of x. This says f of x is less than or equal to g of x. Did I mess up my drawing? No. For all values of x near a. Okay, so as I get close to a, right, somewhere in between my two fingers right now, there should be that condition. And is the red graph g always above the purple graph f in this, just this interval between my fingers, close to a, right, close to a? Yes. So out here we might have, different things happening. But in here, we have to have this true. And that's the interval where h of x has to be. Right, so I'm going to do h of x in green. And h of x may be, out here somewhere. It might not even be between the two functions. But eventually what's going to happen, it's got to get in here. And now, if this is true, we're trapped always between the red and the purple. And I try to move as I can, but I'm squeezed right to the same value. Provided in that interval, I have to stay between these two functions. Same thing from this side, right? As I get close to it, I have to stay between the red and purple function. I'm squeezed down to that same value. So there's the graph of the function h. So you see the squeeze theorem, right, is really close to a. We get squeezed down so that all three functions basically will have the same limit. So provided that, but that's provided f and g squeeze to the same value. Now if f and g both have limits, but those limits are not equal, then we can have a gap, and that means our green function can have a situation where it doesn't even have a limit. We don't even know it has a limit, or it could have a limit, but it may not be equal to either one of the other two. So let's see how this squeeze theorem works. Using a squeeze theorem, is there enough information to determine the limit as x approaches 1 of g of x if this relationship is true for all x not equal to 1? This is only true for x not equal to 1. I can't use x equal 1 into this to get a conclusion. But what I can do is take the limit as x approaches 1 of these sort of boundary functions. So this is kind of like my f of x function from above, 3x plus 1, and this is like my g of x function above. Of course, now the middle function is I'm calling g of x. So the limit as x approaches 1 of 3x plus 1, what's that going to be? Well, again, this says x is approaching 1, so it's never equal to 1. However, 3x plus 1 is a continuous function at 1, and I can plug in directly and get the value of this limit, and I get, of course, 4. Also, the limit as x approaches 1 of this function, right, that's continuous at 1. I can plug in 1 directly, and I get 5 minus 1 squared, 5 minus 1, also 4, right? So what's that tell me? These two are equal. So this tells me that there is enough information to determine the limit, right? And how do we determine it? We say by the squeeze theorem. The limit as x approaches 1 of this function g of x is going to also be 4, because we've got both bounding functions. The limit as x approaches 1 is 4 for both of them. Since they are equal, our limit of our function is also 4. And I've got the graphs of these functions, right? This right here is the graph of the function 3x plus 4. It's a line of slope 3 passing through 0, well, that doesn't look right. sorry, 3x plus 1. I don't know where my 4 came from. 3x plus 1, which now makes sense, passing through the y-axis at x equal, or y equal 1. Of course, I've got a hole there because again, it says for all x not equal to 1, so I don't know what's happening exactly at 1. And, of course, this then is the graph of 5x minus x squared, that parabola opening downward. But you can see as we get close to 1 how we're getting squeezed down. And so the function, our function g, right, is squeezed in between these two, and it's going to go to the same value, right? From both sides, we get squeezed in between there. And so there's nowhere for us to go except towards that hole. Okay. Now, notice if this was the only thing that we were told, that g of 1 was between 4 and 4, which basically means that g of 1 equals 4, right? That is not sufficient to support the conclusion that the limit as x approaches 1 of g of x is 4. That is not sufficient. Okay? G of 1 doesn't even have to be defined. G of 1 could be anything. Right? I can still have all of this is still true, and I can have g of 1 defined to be 2. I can put a point down here. It's not what's happening at 1. When we talk about the limit again, this says take the limit as x approaches 1, says x is not equal to 1. It is less than 1 or greater than 1, right? Approaching 1. So support for this type of problem must show the limit process. What I often see students do is this. This is their support. They just plug in 1 here and plug in 1 here. So that's exactly what you did. Well, no, it's not. Just plugging in, you're wrong, because you can't do that. X cannot be 1. You can't plug in 1 to get these values. But if you're finding the limit as x approaches 1 of these functions, then yes, you can. Those limits are indeed equal to those values by direct substitution, because those functions, right, are continuous for all values of x. And so we know that that's what we're approaching by the fact that they're continuous. So it is important to show the limit notation in your support. Okay, so just be careful about that. It's a little technicality maybe, but you've got to understand what's going on there when we are talking about limits. Let's take a look at one more example. Is there enough information to determine the limit? In this case, we're going to do the same thing. I've got g of x trapped between two functions, again for all x not equal to 1. So again, I'm going to take the limit as x approaches 1 of the bottom function. And by direct substitution, I can find that limit, right? 2 times 1 minus 3 is 2 minus 3 is negative 1. The limit as x approaches 1 of x squared, though, is what? Just 1 squared, which we know is 1. So these two are not equal, right? These are not equal. And so there is not enough information to know what the limit is as x approaches 1 of g of x. It may not even be defined. Here's a picture of the situation. Here's 2x minus 3, the linear function, and here's x squared, the parabola. And you can see at 1, there's holes there. We don't know what's going on exactly there. But our function is squeezed between these two. Yeah, but it's not squeezed down to one single point. So in here, if I let's sort of zoom that area up because it's kind of small. If I sort of open that area up here and see what it looks like, then I have this green function here, and I have this, let's say, purple function this way. But our function, may be coming along, and let's say this is x equal 1 here. Again, we could have holes. We don't know what's happening right at those points. But our function could be coming along here, and as it approaches 1, from this side, maybe we go here and we have an open circle. I don't know, but this side we come here to that situation, right? So the limits from left and right exist, but not equal for our function g. So the limit may not even exist, or it could exist. I mean, they could connect, and the limit could be anything between these two values, these two y coordinates of these holes. So we don't have enough information. We don't know, because they don't squeeze down together to the same value, right? One's 1 and one's -1. There's a gap of 2 units there that we have wiggle room for. So we cannot determine. We don't know. We need more information. Okay, so it would not be helpful in this situation. Okay. Let me show you one more case, and then we'll move on and find that limit we were talking about. This one actually involves a trig function. Let's find the limit as x approaches 0 of x squared times sine of 1 over x. Now, we can't just use direct substitution. You say, well, I can plug in 0. 0 squared is 0. 0 times anything is 0. But it doesn't work that way. Remember, the basic limit laws say the limit of a product is the product of limits, provided each limit exists. The limit as x approaches 0 of x squared exists, it's equal to 0, but the limit as x approaches 0 of sine of 1 over x, remember, does not exist. That was that one that had the infinite number of oscillations as we got close to 0. Okay, so we can't use direct substitution. Now, what we're going to do is to actually use the squeeze theorem. And I start with the fact that sine of 1 over x, I know, for any value of x not equal to 0, is always between -1 and 1. And this is true, right, as long as x is not equal to 0, where this thing is undefined, right? And that's the sine function is always, right, between -1 and 1. It bounces back and forth between -1 and 1. Now, if I multiply all 3 of these quantities by x squared, which is positive, then I get this compound inequality. Right? And now what do I have? I have my function right here, right, in the middle, squeezed between 2 functions, and it's quite easy to see if I take the limit as x approaches 0 of -x squared, plugging in, I get -0 squared is 0, which is the same as the limit as x approaches 0 of x squared. Right? Both my functions above and below go to the same limit 0, and so by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is equal to 0 as well. And basically, graphically, what's going on here, if we want to look at it, is, you know, we've got these 2 functions, x squared and -x squared. X squared is the parabola opening upward, right? Looks like this. There's x squared. And then -x squared is what? Just a reflection in the x-axis, so it looks like this, opening downward. Right? And so what happens as our function is trapped between these 2 functions, x squared sine of 1 over x, well, what's going to happen is it gets close to 0. Remember that sine of 1 over x thing begins to make this thing oscillate back and forth very rapidly, very rapidly. But the problem is it's getting squeezed down at the same time, so that it's even though it's infinite oscillations, it's not going between -1 and 1 anymore, right? It's getting the amplitude. Remember, amplitude's getting smaller and smaller. It's approaching 0. Same thing here. As we bounce back and forth, we're getting squeezed down to 0. And so that is how we can use the squeeze theorem to find a limit of a function that we could not necessarily use the direct substitution with. Okay, in the next video we are going to prove, using the squeeze theorem, an important limit involving the sine function that will come into play in finding limits of other trig functions involving indeterminate forms.